Hi everyone, today I'll be presenting my case study on data security and the Internet of Things. The Internet of Things refers to a network of interconnecting devices that collect, exchange, and process data through the Internet. Examples include smart homes, wearable health devices, industrial automation systems, and smart city infrastructure. As the number of connected devices continue to grow, IoT has transformed the way organizations operate by improving efficiency, automation, and decision making. However, the rapid growth has also increased cybersecurity risks because the large number of sensitive data are continuously collected, transmitted, and stored. Therefore, protecting IoT generated data has become essential for maintaining privacy, organizational resilience, and user trust. The aim of this case study was to critically evaluate data security in IoT. To achieve this aim, I focused on 5 objectives. First, I examine the importance of data security within the IoT environment. Second, identify the major threats and vulnerabilities affecting to IoT data through its life cycle. Third, I critically evaluated the current data security mechanism used to protect IoT generated data. Fourth, I explored future technologies that could improve IoT security. And finally, I discuss the social, ethical, and legal issues associated with current IoT data. IoT data security refers to protecting data through its entire life cycle, including data collection, transmission, processing, and storage. Unlike traditional computer systems, IoT environments consist of many different devices, communication protocol, cloud platforms, and edge computing technologies. This complexity makes security more challenging because data can be attacked at multiple stages. Effective IoT security therefore depends on maintaining the confidentiality, integrity, and availability of data, commonly known as CIA principles. Additionally, security requirements include authentication, authorization, and accountability. Together, these principles ensure that only authorized users and devices can access sensitive information. The literature identify 4 major stages where IoT data are vulnerable. The first stage is data collection. IoT sensors often have limited processing power and memory, making them vulnerable to weak authentication, insecure configuration, and physical tampering. The second stage is data transmission. Data traveling across wireless networks may be exposed to attacks such as man-in-the-middle attacks, replay attacks, and if communication channels are not properly secured. The third stage involves data processing and storage. Misconfigured cloud services, insecure APIs, and weak access control increase the risk of data breaches and unauthorized access. Finally, malware and distributed denial of service attacks continue to be major threats because compromised IoT devices can be used to launch large-scale cybersecurity against organizations and critical infrastructure. And my literature reviews show that although many security solutions exist, no single approach is capable of protecting every layers of an IoT ecosystem. Researchers agree the current security mechanisms are effective under certain conditions, but become difficult to implement consistently. Because IoT devices differ in hardware capabilities, communication protocols, and operating systems. Resources constrain. Devices also struggle to support advanced security technologies. Therefore, the literature continuously recommends adopting a layered defense strategy that combines multiple complementary security mechanisms instead of relying on a single solution. And I evaluated 5 important security mechanisms. The first is authentication and access control, which ensure that only authorized users and devices can access IoT resources. The second is encryption and lightweight cryptography. Encryption protect data confidentiality, while lightweight cryptography provide efficient security of devices with limited processing power. The third mechanism is AI-based intrusion detection. Artificial intelligence can detect abnormal network behavior and previously unseen cyber threats in real time. The fourth mechanism is blockchain technology. Blockchain improves data integrity and transparency by storing information in a decentralized and tamper-resistant manner. Finally, I examine zero trust architecture. Unlike traditional security models, zero trust assume that no users or device should be trusted by default. Instead, every access request must be continuously verified before permission is granted. Although these technologies improve security, each also has limitations, meaning organizations should combine them within a defense in-depth strategy. The future trend of IoT security is expected to shape several emerging technologies. One important development is post-quantum cryptography, which aims to protect IoT systems against future quantum computing attack. Another is federated learning, which allows AI models to be trained without transferring sensitive data to a central server, improving privacy. The increasing adoption of explainable artificial intelligence, or XAI, will also improve transparency by helping users understand how AI systems make security decisions. Together, these technologies are expected to create more secure, resilient, and trustworthy IoT ecosystem. IoT ecosystem is not only a technical issue but also a legal and ethical responsibilities. IoT devices continuously collect personal and organizational data, often without users fully understanding how those data are processed or shared. This raises concerns regarding privacy, informed consent, and accountability. Organizations must comply with regulations such as the UK GDPR and the Data Protection Act 2018. They also need to implement security by design principles and recognized cybersecurity frameworks, including the NIST cybersecurity framework. Using explainable AI can improve transparency and increase the trust by making automated security decisions easier to understand. And in conclusion, IoT technologies continue to transform industries by enabling automation, real-time monitoring, and data-driven decision-making. However, these benefits are accompanied by significant cybersecurity challenges. My case study found that while current security mechanisms such as authentication, encryption, AI-based intrusion detection, blockchain, and zero trust architecture all improve security, none provide complete protection independently. Future technologies include post-quantum cryptography, federated learning, and explainable AI, offer promising opportunities to strengthen IoT security. Ultimately, organizations should adopt a layered security approach supported by effective governance, continuous risk assessment, and responsible data management to build secure, trustworthy, and resilient IoT ecosystem. In the end, I would like to thank Dr. Haider Ali, and thanks for listening. Bye.